So this is section 8.3, and this section is on trig integrals, specifically ones that involve sine and cosine and secant and tangent. These are a little bit different than what we have done in the past, in that you can't make a nice u substitution from the beginning. You have to manipulate it a little bit to get it into a form where you can use a u substitution. So let's just dive right into the first example here. This one we have sine cubed x and times cosine to the fourth x dx. The fact that this is an odd power is going to be important to us. That's because even powers are helpful because we have this thing called the power reducing formulas, and we can use those on even powers. So we can use, we can write any even power as like a squared to, some power there. So let's just look at this odd power here of sine. We can break this up into sine times sine squared. Now the good thing about doing that is that this sine squared, we can use a Pythagorean identity. From over here, we have sine squared plus cosine squared equals 1. That means that sine squared is 1 minus cosine squared. Now here's what this just did, okay? I took that sine cubed, I rewrote it as sine to the first times sine squared. Then I rewrote sine squared as 1 minus cosine squared. The benefit of doing that is that now I can let u be cosine x, and then this extra sine x hanging out here is my du. My du is actually negative sine x, but it gets absorbed into my du. So the whole idea behind this, and I will state this on the next page, is that when you have integrals involving sine and cosine, that if you have an odd power, you kind of put one aside for your du, and then the other one you can use either like a Pythagorean identity or, if necessary, a power reducing. But the Pythagorean identities are a lot nicer to use if you can use those. So yeah, let's let u be cosine x. Du, of course, is negative sine x, so I just divided both sides by negative 1. And then look at what this integral becomes. We get this negative right here. So this negative is right there, and of course that came from that derivative. Okay, I'll forget. This would be 1 minus u squared, and this will be u to the fourth, and then of course this is my negative du. So distributing that out, that gives me u to the fourth minus u to the sixth. And then if I just go ahead and distribute this minus, just so I don't have to contend with it much longer here, that's going to make that negative u to the fourth plus u to the sixth, which is the same thing as u to the sixth minus u to the fourth. All right, integrating this, piece of cake, right? U to the 7 over 7 minus u to the 5 over 5 plus c. And then we just put back in for u. We just substitute back in that cosine for u. So here's the rule. If you have an integral involving powers of sine and cosine, and one of the powers is odd, you're going to separate this odd power into two parts, one of which is going to be your du, and the other is going to be replaced by a Pythagorean identity. Right? So that odd power, we're going to separate one of them off to the side for your du, and then the other one we'll be able to use a Pythagorean identity on. Okay, so let's look at another example then. Sine and cosine, and check it out. We've got that odd power, so that's the one I'm focusing on. So I'm going to rewrite it as cosine to the first and cosine to the fourth. Now I did that first, now I did that on purpose, right? I did that first power on purpose. I did not split this up into like cosine squared and cosine cubed. I did cosine to the first, that's going to be saved for my du, and then the cosine to the fourth. This cosine to the fourth, I need to change this into a function involving sine. That way, just like last time with example 1, I can let u be sine and then my du be cosine. But I need this to be a function of sine there. So what can I do? Well, I said that I was going to use that Pythagorean identity whenever possible. But it's a fourth power, and my Pythagorean identity only works for squares. That's okay. Look, the fourth power is just a squared squared. So I just chose to write it as squared twice. I could have written cosine squared x quantity squared. Alright, so using that Pythagorean identity, cosine squared is 1 minus sine squared, cosine squared, 1 minus sine squared, and I just threw this cosine x out here just because I know I'm about to make my substitution, and I just kind of wanted it grouped over there because it's gonna, all that's going to be my du. Okay, so I'm going to let u be sine x, so du is cosine x dx. So this is going to become, of course, a u squared, a 1 minus u squared, another 1 minus u squared, du. And then we just need to multiply all that out. So I just multiplied this out first. So I'm going to grab a different color. So if you multiply that stuff out first, you get that just from distributing. And then I distributed that u squared throughout there. So in distributing that u squared, I end up with some crooked paper here that's, alright, so oops, can bring that back to it. Alright, so then I just have to integrate these. Okay, each one of these integrate nicely, right? They're just the power rule. And then all you have to do is go back here to where u was sine x, and then I'm just going to put sine x back in for all of those u's. So with examples 1 and 2, both of these examples utilized this rule. So this is the rule for integrals involving sine and cosine where one of the powers is odd. Example 1, I had an odd power on a sine function. Example 2, I had an odd power on the cosine function. But they acted very much the same. Example 3 here, I don't have an odd power. So I'm going to have to utilize the power reducing formula. Now this is on your formula sheet as well, cleverly labeled with power reducing formulas. So I'm utilizing this power reducing formula of sine squared u is 1 minus cosine 2u all over 2. Now it's called a power reducing formula because it does just that. It's going to reduce this exponent. It's going to take this from being a squared to no longer being a squared. And all this is an algebraic manipulation of the double angle formula for the cosine function, just in case you're wondering. Okay, so if I take sine to the 4th power and rewrite it as sine squared squared, I can replace this pink sine squared 2 theta with the double angle. So I tried to color code this for you so you could see that this pink stuff here, I'm replacing this sine squared. Now remember, this formula right here is sine squared u. So in this case my u is 2 theta. Right, that's my argument of the sine function. So it's sine squared 2 theta And then we have this outer squared that's going to give me my fourth power here. Okay, so all of this becomes this from the power reducing formula. So 1 minus cosine 2u, in this case my u was 2 theta, all over 2. Alright, so let's do a little cleaning up here of this. Let's do a little bit of algebra here. Of course that's going to be 4 theta. You can see I pulled out a 1/4 right here. Do you see where that came from though? How did I suddenly get a 1/4 out of here? Well, this fraction squared is the top squared over the bottom squared. So this stuff squared is right here. This 2 squared is 4, and I just factored that, or I just pulled that constant multiple out to just kind of get it out of the way. So I just have this integral of 1 minus cosine 4 theta quantity squared. Okay, of course, something squared is that thing times itself, and then I'm just going to multiply all of that out. So when I start distributing that out, I'm going to get this stuff. Right? So that came as a result of distributing out 1 minus cosine 4 theta times 1 minus cosine 4 theta. So it's 1 times 1, 1 times cosine 4 theta, negative cosine 4 theta times 1, negative cosine 4 theta times negative cosine 4 theta. Okay, so I distribute that stuff out. Alright, so I've got, you know, the integral of 1. Okay, I can integrate that, no big deal. 2 cosine 4 theta, not a big deal, I can integrate that. Ah, I got a squared. Those squares are the problem. That's what I was trying to get rid of. So, I got to use the power reducing formula again. This time I'm going to have to use the cosine power reducing formula. So this cosine squared u is 1 plus cosine 2u all over 2. So I still got my 1/4 hanging out there, my 1, 2 cosine 4 theta. This is the cosine power reducing formula. In this case, my u is 4 theta. So using the cosine power reducing formula and putting 4 theta in for u, I get this. Alright, let's clean it up. So this stuff right here is going to be 1/2 and then cosine 8 theta over 2. I'm just going to go ahead and add those constants. 1 plus 1/2 is 3/2. Alright, so now I've got 3 separate integrals going on here. I've got this 1/4 times all of these, so it's 1/4, and we've got the integral of 3/2. No big deal. 1/4, and then we got this integral of minus 2 cosine 4 theta, and then we've got the 1/4 and the cosine 8 theta over 2. Alright, so that one's just going to be 3/8 and then the integral of d theta. Okay, that's just going to be theta. This one, 2/4, is the same as 1/2, so I just have to integrate cosine 4 theta. And then taking this 2 out, it's going to give me a 1/8, and I'm going to integrate a cosine 8 theta. This is the easiest one, so let's do it first. That's just going to be 3/8 and then the integral of basically 1 with respect to theta is theta. This one, you might need to do a u substitution, you might not. You might be able to do that u substitution kind of in your head. It just kind of depends. But if you let u be 4 theta, then du is 4 d theta, divided by 4, you get a 1/4 du. So that becomes cosine u du. We've got this 1/2, and then this 1/4 came from that substitution. So that basically becomes a, a 1/8 sine 4 theta. Over here, I didn't do the substitution. I just kind of went ahead and kind of did it in my head, you know. You know, from the chain rule, if you were taking the derivative of this, you would take the derivative of cosine, right, which is what, sine, negative sine, yeah. And then you would multiply it by the derivative of 4 theta, right? The integration here is kind of the same, right? That you're integrating that cosine, and instead of the chain rule being multiplying by 4, you're dividing by 4. So that's essentially what we're doing. So here I integrated cosine and got sine, and then divided by 8, kind of undoing that chain rule. And then this 1/8 was already there. That came from the 1/4 that's just been kind of drugged along with us the whole way, and then it's over 2 from the power reducing formula. So that gives us a final integral here of 3/8 theta minus 1/8 sine 4 theta plus 1/64 sine 8 theta equals C. So I did skip the U substitution here. I kind of reasoned out here that, hey, this is going to be the exact same thing, only I'm not going to have a 1/4. I'm going to have a 1/8 because that's an 8 theta. If you need to do from here to here, if you need to let U be 8 theta and go through that, go ahead. Okay, so the next few examples are going to use secant tangent stuff. So remember, the derivative of secant is secant tangent. The derivative of tangent is secant squared. The next few examples are going to show you how to integrate secant tangent integrals. They're not quite as straightforward as the sine cosine ones. So we do have three versions of the Pythagorean identities. We have the sine squared plus cosine squared is 1. And why does that look kind of blurry? And then we have this 1 plus tangent squared is secant squared business. That's going to be really helpful, okay? So that one is going to be super duper helpful for us. Okay, so our next rule. If the exponent on secant is positive and even, then you're going to keep secant squared for du and use a Pythagorean identity to rewrite the others. So we're going to keep a secant squared for du. This is a little tougher because those derivatives are a little messier. You know, with sine and cosine, those derivatives are, you know, kind of nice, right? But with this one, you got to remember that, you know, the derivative of tangent is secant squared. The derivative of secant is secant tangent. So, if the exponent on secant is positive and even, then we're going to keep a secant squared for du, and we're going to use the other even part of that secant and a Pythagorean identity to rewrite it in terms of tangent. And then we'll let u be tangent. All right, let's see it in action. So we're going to evaluate tangent to the 4th times secant to the 4th. All right, so sure enough, we've got an even secant. So I'm going to split it up into 2 squares. One of those squares is going to be saved for my du. because I'm thinking ahead, then I'm going to let u be tangent. The derivative of tangent is secant squared. So I'm going to need this secant squared for my du. This other one, I'm going to use the Pythagorean identity here. So I'm using this 1 plus tangent squared equals secant squared, Pythagorean identity. All right, and then we're set up for our u substitution. We'll let u be tangent. Du is secant squared, so all that gets absorbed into your du. So we end up with just a nice little u to the 4th times 1 plus u squared du. And multiplying that out, and all we have to do is use the power rule to integrate u to the 4th and u to the 6th, and then substitute back in for tangent. So these are pretty straightforward. The whole goal for all of these is all about setting aside something for your du and manipulating what you have left, with Pythagorean identities to make all of those in terms of the other function. All right, so here's another case that we run into. If the exponent on tangent is positive and odd, the last one was even, then we're going to take out one tangent to put with a secant so that we have that secant tangent for my du. Then we use Pythagorean identities to rewrite the other ones as other tangents as secants, and we'll let u be secant x. All right, let's see this one in action. All right, so we've got an odd exponent on this tangent. So we're going to split that up into a tangent to the first and a tangent squared. Now you'll notice that I did go ahead and rewrite this square root of secant. I brought it up top and made it into an exponent, so it's a negative 1/2 power. My tangent to the third, I split into tangent squared and tangent x. So remember, we're looking to have u be secant, in which case du would be secant tangent. Oh, well that's weird, because if I let u be secant, I don't have another secant to put with this for my du. See what I'm saying? If I go ahead and replace this with the Pythagorean identity, it almost looks like I don't have enough secants to go around. And you're right, I don't. So I'm going to have to compensate for that. Okay? And this is where it starts getting really weird, because it looks like I'm just, using some dark magic or something. I'm just making stuff up as I go. This blue stuff right here, this secant to the negative 1/2 power, look at how I split that apart. I split it apart into secant x and secant to the negative 3/2 x. Remember, when you multiply two things, when we talk about exponent laws, multiplying with the same base, you add the exponents. So 1, the exponent of 1, plus negative 3/2 is negative 1/2. Now, how on earth did I even know to do this? Well, I needed a secant. Because if I'm going to let u be secant here, I need a secant for my du, because I need secant tangent. This was not pretty to have to split up. And I chose this specifically for this reason, because that square root was not pretty. In some of the examples, you may just have like a secant squared. Okay, well that's easy enough. It's just secant times secant. If that were like a secant to the 5th, okay, you take out one secant and that's a secant to the 4th. But I picked this one specifically because it was uglier, and I wanted to show you how to deal with an uglier example. So I needed secant to the first, so I needed 1 plus what number is going to give me this number. So that's where this negative 3/2 comes in. Now, I can replace that tangent squared with its Pythagorean identity. The Pythagorean identity is 1 plus tangent squared is secant squared. So if you just subtract 1 from both sides. Now you can see that secant tangent, that's going to be my du. And then everything else that's left is going to be in terms of u, or just secant in this case. So all I did was rewrite some terms. I moved my secant tangent to the end, and I put this secant to the -3/2 over here, because it's time for my u substitution. U is going to be secant x, so that's going to be a u squared minus 1, and then u to the -3/2, and then all this is going to be my du. So all this mess that I did was all just to be able to evaluate this, because I couldn't just do a straight substitution from the beginning of just, hey, let's let u be secant and du is this stuff. Okay. So making that substitution in for u, I get this, and then of course I'm going to distribute that out so that I can just have to use the power rule for the integration. So remember, when you're multiplying with the same base, you're adding the exponent. So that's 2 plus -3/2 is that 1/2. And then, of course, that times 1 is just itself. And then just using the power rule. So I'm just going to add 1 to that and then put it over that number. So that's going to be u to the 3/2 divided by 3/2. Adding 1 to this is going to make that u to the -1/2 divided by -1/2. Be careful, there's a lot of negatives happening in here. So then that's going to become a positive, and then just putting in back in secant x for u. This is a kind of a messy one to have to do. Okay, let's look at the last case. The last case that we're going to look at is if the integral contains only tangent and its exponent is even. Now there's a whole bunch of different kinds of rules for these, but these are the primary ones that we're going to focus on. Okay? So if the integral contains only tangent and its exponent is even, we're going to rewrite a tangent squared as a secant squared using the Pythagorean identity, and then we're going to let u be tangent so that that derivative is secant squared. This one's a little more straightforward than the last example. So tangent to the 4th, just a tangent, and it's an even exponent. So we're going to split that apart into 2 squares. I'm going to replace one of those tangent squares with its Pythagorean identity. And then I distributed that tangent squared out. Okay. Now, here's the nice thing that comes out of that. This integral over here is actually quite nice, because I can let u be tangent, and then there's my du, secant squared. Over here, I got a tangent squared. What am I supposed to do with that? Well, let's use the Pythagorean identity again. So this integral's okay. We'll be back for you. But let's go ahead and use that Pythagorean identity again on this one. So it's kind of the same thing I did for that 4th power. Let's just keep that party going here. So we've got Pythagorean identity. Now, how does that help us by putting that Pythagorean identity in there? Well, this one we said was that this integral was pretty nice. It's a u substitution. I can let u be tangent, and then this secant squared dx is my du. So this will just be the integral of u squared du. How is this one nicer than tangent squared? Well, we can integrate secant squared pretty easily. Okay, let's see if that's on your formula sheet. Yes, it is. I wasn't sure if it was. Look, the integral of secant squared is just tangent. Well, yeah, because the derivative of tangent is secant squared. So that's a really nice integral. Secant squared, that's a pretty easy integral. The integral of 1, pretty darn easy as well. So that's going to be that u squared du from that u substitution. So power rule, u cubed over 3, substituting back in for tangent. This one, the integral of secant squared, we said was just tangent. The integral of 1 is just x. Now look, this subtraction right here, this subtraction was for this entire integral. It was for that tangent squared, so it's for this entire thing. So it's for both of these. So that minus is going to go for both of these, so it's going to get distributed throughout there. The integral of secant squared was tangent, the integral of 1 was x. That subtraction there from the Pythagorean identity, and then distributing that minus throughout is going to make that a minus tangent x and then a plus x plus c. Alright, I know this can be a little confusing, but I hope that having those rules in place and an example of each scenario will help you with this section. So, alright, that finishes up section 8.3.